if virtual particle pairs are equal in mass, how does a black hole lose mass if one falls in? How does the escaping particle get enough energy to escape the clutches of extreme gravity? Okay, I'm going to give you a scenario, completely theoretical scenario, and not entirely accurate that this is how it happens. But imagine this situation, okay? It's not entirely accurate, but it's a good analogy to give you to kind of understand how it happens. You have a black hole, okay? Whatever size it is, a black hole of mass m. It has a horizon which is called the event horizon. That is the boundary of no return. So here is the black hole center, here is the black hole, and if you cross the event horizon, then you will never return. So let's say you are right at the boundary of no return. And because of the incredible gravitational strength of the black hole, or not because of it, just randomly, a virtual particle antiparticle pair is formed. See, space isn't empty. Quantum field theory tells us space isn't empty. It's teeming with these virtual particle antiparticle pairs that don't quite break the laws of physics. They obey Heisenberg's uncertainty principle. The time version, not the energy version, the time version. So you have a particle antiparticle pair that is formed spontaneously and it's going to collapse again. And nothing will be changed in the universe. But this particle antiparticle pair, it has been formed because of the gravity of the black hole. So the energy bill of the formation of the particle antiparticle pair is footed by the black hole. Okay, so some of the black hole's energy, mass energy, is converted into a particle antiparticle pair, which in regular circumstances would once again merge together and nothing will happen and the black hole loses nothing. But because this happened at the event horizon, one particle goes into the black hole and another one escapes. So this virtual particle antiparticle pair becomes a real particle antiparticle pair because one is lost inside the black hole and one goes outside. And because the mass energy bill was footed by the black hole shrinks in mass. That's what happens. That's kind of how you can see it. It's a very rough and rather imprecise analogy, but that's how it happens. That's how we can think of it happening. So the particle pairs are obviously both the particles are equal in mass, but they have opposite signs, right? Particle antiparticle, opposite quantum numbers. So that's how the black hole loses mass when one falls in. It would not lose mass if both fell in, but one escapes. And that mass was actually the mass of the black hole. So that's what happens, all right? And that's the phenomenon of Hawking radiation. The black holes appear to radiate, radiation coming out. And the radiation exhibits a black body spectrum, completely random. So that's how a black hole seems to have temperature and radiation, and that's how it loses mass. Black hole evaporation, Hawking temperature, and Hawking radiation. That's how it happens. All right.